All right, so it looks like we have sound and recording. I'm going to continue with some additional exercises from shear force and bending moment diagram on beams. And one problem, say, could be representative is this one. With a cantilever and taper distributed load, say you have a overhanging roof with sand, rather snow on it. Not that it happens too often in this part of the country. Okay, so let me sketch the problem. So again, we're going to do 73. We have the taper, that's the cantilever, and we have the taper force that goes from 8,000, or rather 84 kilonewton per meter goes to 0. Okay, and we have the span of the cantilever is 2.4 meters. We want to draw the shear force and bending moment diagrams. Okay. So, well, I thought I'm turning this off. Blank screen. It goes back to where it's slow responding, maybe. Okay, so you know that from statics that the effect of a distributed load upon the support is the same as that of a concentrated force equal to the area of the distributed load applied at the centroid of the shape. And I'm sorry? I think it was 73. Yes, 73. Is it 573? And so we have a distributed force that is equivalent, or its equivalent is a concentrated force that's equal to this area. So F, again, they don't act this simultaneously. So this force F is going to be the area of a triangle, and it's going to be 1 over 2, 8.4 multiplied by 2.4. Okay, that's the magnitude of the equivalent force when it comes to the response of the support, but not the response of the beam. So 8.4 times 2.4 over 2, and this is 84.672 kilonewtons. As for its location, it is 1/3 and 2/3, so this will be 1 over 3 times 2.4. Okay, so 2.4 times 2.4 over 3, this is 0.8. I said 0.8 meters. Okay, so now we can calculate the reaction of supports. It's going to be the calculated equivalent concentrated force on one hand, and then we have a moment is going to be this force equal to its harm 0.8. So if I take the support off, I'm going to see a force that is 84.672 kilonewtons. And then, as you can see, the whole beam, now that it's off support, has a tendency to rotate clockwise. I need to introduce a moment that is counterclockwise and equal to this force times the arm. All right, so 0.8 times 84.672 equals, that's 67.7376 kilonewton meters. All right, So let's draw the shear force and the bending moment diagrams. Shear force is going to be in kilonewtons, and we know that once we move to the right, we experience this force, the 84.672 kilonewtons. Okay, so 84.672 units here. And then we have, remember, these are like distributed forces pointing down. So what they do, they cause the shear force to decay. And because we have linear, this is going to be parabolic, going to zero from the maximum value. And the slope of the parabola, again, this is negative value and diminishes. So the slope of the parabola will be a negative one. This is positive slope. This is a negative slope. So it goes from a maximum, which is this piece, to zero. So I'm showing this is going to be the shear diagram. All right, and the moment diagram M is going to be in kilonewton meters. Once you calculate, you'll do a stress calculation, of course, you switch to more convenient units, say Newton millimeters. Anyway, so on the moment diagram, now the beam is going to be thrown. So clearly, it means that the entire moment diagram is going to be below the x-axis and begins with a drop. It says that this is external. So if I take the beam, reaction moment at the support is going to be a negative moment. So or at a counterclockwise moment. So this causes the diagram to drop by what amount? 67.7376. 67, it's a negative value, 7376. Okay? And then what it does, it goes to zero, and I read the slope. This was a second degree curve. Moment is going to be a third degree curve, and we're going to see the slope of the curve going from a steep positive value to zero. Okay, these are positive values. So it's a cubic that goes from maximum slope to zero slope. All right, so this is parabola or second degree curve. And this is going to be a third degree curve. Okay? Now, if we want to write equations of the two curves, we can do it by via integration. So we have dv over dx, and x is measured like origin here and positive to the right. dv over dx is w. And then I say for moments, I have dm over dx is v. So I can move to integrating. Again, will be like a current x value starting from 0. I don't know how to put it, or where should I put it where it's best. All right, so x to the current value. I want to know how big is this, how big is this. No, what to be the middle?
Is that line like in the middle of
the 2.4? No, it's just an arbitrary value that goes between 0 and full length 2.4. All right, so we're going to integrate. So it's going to be dv going from 0 to x equals integral from 0 to x of concentrated, or rather distributed force, sorry, dx. In this one, 0 to x, m, or rather dm, equals integral from 0 to x v dx, and I have to have constants of integration, constant 1 and constant 2. Okay? So I need to write the equation of the, what is w? if I'm, at x, say, so where is x? Like here. What is w as function of x? It's what I need to start with. Okay. I'm missing a, no, just a cap. Okay, so what is this equation? I start from 8.4 kilo, so it's going to be 8.4 in kilonewton per meter. And then it goes to negative, and what's the slope? The slope is 8.4 divided by 2.4. 8.4. So this is negative 3.5. 3.5 times x. Okay, so if x is 0, I have this piece. If I make x 2.4 is going, this goes to 0. Yeah, linear relationship. So yeah, 8.4 negative 3.4 times 2.4. I'm sorry. So 8.4 I said negative 3.5. Yeah, 3.5 times 2.4 equals 0. So yeah, this is the equation. This is the one that goes here. So let's see what we have. We have integral. This is going to be what? V at x minus v at v of x minus v of 0, which I know v at 0. What is v at 0? It's is this value. Okay, and it equals to, now I integrate from 0 to x of 8.4 minus 3.5 times x dx plus c1, right? So I'm interested in v of x. Let me write above. So v of x is going to be the 84.672. So I move this to the right, and then I have plus, and it's going to be 8.4 times x minus would be 1 over 2 or 3.5 divided by 2 times x squared going from 0 to x plus the constant of integration, c1. Okay, so again, I'm moving up with my analysis. So this one is going to be, if I take of 0, this is 0, this is 0, so it's going to be v of x equals, and let's move the second degree term first. So it's going to be 3.5. What is 3.5? 3.5 by 2, that's 17, negative 175 x squared. And then I have plus 8.4x. And then I have plus 84.672 plus C1. Okay. Okay. So how do I clarify what C1 is? I know that, so further up, C1, I know that V of 0 equals the 84.672 kilonewtons, and then V of 2.4 is going to be 0, all right? So from the first equation, what do we get? Actually, it's over-constraining. I have one unknown, and I wrote two equations. So if I make 0, this is 0, this is 0, it's clear that C1 has to be 0. Is that correct? So, and then if I make this 2.4 with C equals 0, so E equals 0 has to be equal 0 from the first condition. Do I get it 0? So negative, let's say 1.75 negative times 2.4 squared, and then plus 8.4 times 2.4 equals, no, do I have it right? So I said 1.75 negative times 2.4 squared, that is, and then I have plus 8.4 times 2.4 equals, it's 1008. And then plus this one, does not go to 0. Unless we missed something. So, this one is wrong? Okay, so yeah, it makes sense because of what I get. It's 10.08. 10.8. So this calculation is wrong. Thank you. Yeah, it's what I have it here, 10.8. So 10.08 is this one, 10.08, and with this value, I get it goes to 0. C1 0. This is 0 at 2.4. The mistake was there. I'll correct it. So again, 10.08. Anywhere? Yes. And then here, yeah, this one is wrong. So 8.5, I don't know what I did. So 0.5, it's a Monday after the weekend. 0.5 times 8.4 times 2.4 equals 10.08. Yes, it's what I was expecting. All right, so fixed it. All right, and so yeah, we've got it, 0. And then if we want to get the moment equation, again, we expect a cubic. Where's going to be a cubic? So I have what? It's m of x negative m at 0. And this is equal to integral from 0 to x of v. And v, the equation of v is going to just be this one. So negative 1.75 x squared plus 8.4 x plus 10.08 dx plus the second constant of integration. M at 0, I know it. M at 0 is this, and of course this is a bad value already. So let me fix it. Again, we said it's 10.08, and this one is going to be 10.08 times 0.8, and this is 8.064, negative 8.064. So this is what we have here. So it's negative, negative. Again, this just by itself, it's 8.064. And I cannot slide this up. So I have m of x, okay, and I move this to the side. So negative, negative, positive goes to the right, becomes negative again, 8.064. Okay, and then I have, let's see what these are. So it's going to be negative 1.75 over 3x to the power 3 plus 8.4 over 2x squared plus 10.08 times x going from 0 to current x plus the second constant of integration. For going from 0, this whole thing becomes 0. So I have, where can I write it? Maybe here. So I have m of x is going to be, let me put the cubic term first. So 1.75 over 3, this is not too bad. So 1.75 over 3, 1.75 over 3x cubed. And then I have plus 4.2 x squared. And then I have plus 10.08 x, this piece here. And then I moved last the negative 8.064 plus C2. Okay, How do I get C2? From the limit conditions. The moment at x0 has to be the what? This one. So if I make x0, I get this. It means that C2 has to be 0. If I make x equals 2.4, this whole thing has to go to 0. It should confirm. So yeah, we can verify. Again, this comes from stating that m at 0 equals negative 8.064, and m of 2.4 is 0. So from the first condition, we got this 0. Let's see if with the 0, this goes to 0. So I have 1.75 negative over 3 times 2.4 at power 3, okay, plus 4.2 times 2.4 squared plus 10.08. I pressed the equal sign too early. I need to start over. So 1.75 over 3 equals, and this has to be negative, times 2.4 at power 3 plus 4.2 times 2.4 squared plus 10.08 times 2.4 negative, there's something, 8.064. Does it come 0 if I make x equal 2.4 in this equation? Can you help me here? I have a tendency to drift. So 1.75 negative over 3 times 2.4 at power 3 equals plus 4.2 times 2.4 squared plus, unless we missed the sign, and I said that, oh yeah, plus 10.08 times 2.4 equals, it keeps on going up. Maybe I missed a sign somewhere. Huh? Okay, negative. This one was negative. So negative, negative. Again, it's not confirmed that m of 2.4 is 0, like we have it on the graph. So maybe I missed a sign somewhere. Was it a negative somewhere? It was negative, positive. And when we integrated, so over 3, over 2, it was 4.2. Was it 4.2? Yes, this is fine. And then C2. When I make x equals 0, I get this, which is this. When I make x 2.4, I should get 0. And it doesn't seem to go to 0. Were you able to find a mistake? Or maybe I missed calculations again. Anyway, so last time after you left, I verified it was similar type of conditions. And for the last problem that we did, is it I'm
so if m of 0 equals negative 8.064, then the first 3 terms turn into 0.
Well, this is when x equals 0. Moment is this one. When you make x equals 2.4, that is the left or the right hand end of the beam, and from the first condition, this should go to 0. You should have everything equals 0. So if I make 2.4, 2.4, 2.4, it should go to 0, according to confirm the diagram. And okay, so this was negative, negative, went positive, yeah, negative. I don't know why it doesn't come up as we expect. But essentially the master equations are these. You integrate, don't forget the constants of integration. You clarify constant of integrations from the end conditions. And otherwise, if we want somebody has like in the middle of the beam 1.2, how big is the moment? Okay, so how do you get that? Yeah, well, you'd have to at least integrate from 0 to 1.2 to get this area to find this moment. If you have the moment equation, of course, you just put x equals 1.2 in the moment equation, and it gets you the moment. But otherwise, you can use area. So this was verified. What was it? This was verified. And to find the bending moment at the middle of the beam, I need to integrate v between 0 and x equals half of this. This is 1.2. This is the way of doing it. The appendix was the parabola. Some engineering tables list like how to calculate the area under a parabola between 2 points. This one doesn't have it, but we can find online like area under of parabola between 2 points, and it's canned formula you can use. Okay, let's. So this was one. Let's look at. I'm blanking this. I can go back to the recording and verify, clear mine or. Oh, this is ours. All right, this is ours. Let me blank this. So nobody used this room. This is ours. Last problem we did, and I verify these. So yeah, they were, this is. We're missing a few lines. So yeah, it was all complete and correct. Let's do a problem. So now I'm going to erase this. You maybe step away to where camera can record the image, and let's do a problem with branch branch beams. So let's see how we handle one of those. And you take a short break to bring you I printed cover copies for the homework that I sent you via email. You've got my email with the homework that you need to use AutoCAD. You can use whatever CAD package you want, but AutoCAD is, I'm explaining how you can use AutoCAD, but you can use Inventor too for the same purpose. Okay, so let's.
Real quick, could you mind looking at this, just looking at kind of the strategy of how to solve, let's say, P540, but it gives us 2 moments on either side of it, and finding.
So you asked me about a specific. You tried one P540. This one? Oh, you did this one in class.
I'm sorry, my numbers on here.
It should be 40.
Haven't we done this in class? So you want me to look at the problem, at the specific problem that you tried?
48. My book.
48. Okay, let's look at 48.
Yes, that's the one.
This one?
Yes, sir.
Okay, 48 has concentrated forces and moments on top of a distributed load. Yeah. Okay, this is a problem. So for this, I need to. What will be the way of doing it? I did this before. So print print screen, and then go to Paint, paste, and then you said this problem. And where will be a good place to put it? And I need the board below. And I need to erase some space. Okay, so in addition, we have concentrated moments, as you can see. But this beam, this beam has symmetry. So we're going to exploit a symmetry, save us some calculation time, right? So on one hand, the moments are equal and opposing. So they don't condition the reactions of the support. And then the distributed load is symmetric and concentrated force is symmetric. I'm just trying to, so this is problem, all right. Let's see. So firstly, we need to find, let's call this point A, B, C, and D. We need to find reaction at A and the reaction at D. All right. Because of the symmetry that I was telling you, I'm not going to go through all the some moments, whatever. And I'm just going to say down force divided by 2 is going to be RA and equal to RD. So if I'm to sum forces in the y direction or vertical direction, I have equilibrium. And again, the two moments being equal and opposing, they cancel each other's effect, and there's no change in the reaction force of the A and D. So what do we have? We have, again, distributed forces are, everything is down. So RA, and on top of them, because of RA equals RD, the second equation. So RA positive, negative, it will be 1, and we'll work on kilonewton meters. So 1 times 0.24, and then I have 2 times 0.6, and then negative, repeat this 1 times 0.24, and then plus RD equals 0, all right? So I could just say 2RA and everything else. So RA from here equals RD, and it's going to be, this moves to the right, positive becomes positive. So 0.24 plus, this is 1.2 plus 0.24, could have said times 2 divided by 2 equals, why not leave it as is? So 2 times 0.6, make our life easy. So I have a 2 here, so it'll be 0.6 times 0.24, so 0.684, okay, kilonewtons. Confirm that this is a correct value. Is it? Should be. All right, so I have 0.84 kilonewtons, 0.84 kilonewtons. Yes.
So, are those on the outside? Is that trying to show a moment, or is it just saying that those squares are 1 kilonewton per meter? I thought a moment was kilonewton.
Oh, you're very right. It just says, okay, so still haven't done any mistake. I need to retract some statement that I made. I said that if these are moments, they cancel each other effect. You're very right. So they are not moments, you just say what the magnitude is. So I said, yeah. So no mistake here. It's just that these are not moments. So it won't show on the moment diagram.
But wouldn't they still increase the
No,
reaction
no.
forces?
Because of symmetry. So they don't, I mean, in this, I took 1 and it's here, and 1 it's here. So this equation is correct. What I missed though, again, I haven't practiced this problem anyway, so I missed these 2. So I need to add 2. This is not correct. So I need to add to this negative 450 negative 450 equals 0. Okay, so RA plus going 2 and then everything, so I need to say times 2 or 2 times 450 divided by 2. So what do we get? What was before? So 2.4 plus 0.6, 0.24 plus 0.24 plus 0.6 equals, and then plus 450 equals. This is, oh, those are newtons. So yet another place of possible mistakes. So this has to be, if it's kilonewtons, yeah, too much discrepancy, 0.45. Okay, to have everything in kilonewtons, I need to start over. 0.24 plus 0.6 plus 0.45 equals, that's 1.29 kilonewtons. Is it what you have? You said you tried this problem on your own. 1429. This is statics. This is not my class. Kilonewtons. I'm going to show you how to draw the diagram, shear force and bending moment diagram. But when it comes to force analysis, this is something you know from a different professor. Do these verify to your calculation? Now you're the lead. You know, I'm the public that claps or tries to, you know, karaoke.
Correct. I think,
Thank you.
overcomplicated. I thought those were moments on either side.
No, they're not moments, and I thought you know, I likewise, I thought it's more complicated than it is. So let's draw the shear diagram. We have the 1.29, positive 1.29. Again, this is V, and it's in kilonewtons. All right, and then I have a nothing changes, or at a linear variation or decrease by a slope of 2. Or at a 1 kilonewton per meter. And where do we get? We need to know the amount of shear force at point B. So for that, I'm going to say V at B is going to be 1.29 minus 0.24 times 1. All right, so this remains positive, is going to be 1.05. All right, 1.05. 1.05. And then I have a drop by this is 0.45 kilonewtons. 0.45 kilonewtons. So I have a drop of 0.45. So 1.05 minus 0.45, it goes to, come on, I multiplied. 1.05 negative 0.45 equals 0.6. Okay, drops to 0.6. This diagram is too tiny. Let me exaggerate a little bit or increase. So 105. And then I have a drop to 0.6, 1.0, what was it, 0.05? And 0.6. Okay, and then it goes to a steeper slope. It has to be, due to symmetry, moment has to go to 0 in the middle. Okay, so, and like the diagram likewise is going to be a symmetric diagram. And this is 1.29 negative. This is negative 1.05 and 0 in the middle. Is it clear how I got the, oh, I said it's a drop. I'm sorry. So for a drop, it has to go this way. There's a step. And the step here is equal to 0.45 because of this. Does it make sense? All right. So I start with RA, go linear, negative slope, this much slope. and then I have a drop of 0.45. I evaluate right before point B the amount of shear by just taking this area. Yeah, or summing moments, not just the area, but I have the reaction. Okay, and then you either go from right to left, change signs, or you keep on going. I have the shear diagram. And then for moments, this beam is smiling, so I know moment diagram is going to be kilonewton meters, is going to be all positive, moments will be all positive. Okay, so they are parabolas, they are flexed at the location. So I have a, what? Looking at the slope. So starts steeper and goes to this value here. And then I have a, you have a curved beam that you flex, and it goes like, it changes slope, but goes smoothly. And then goes like so. So this change here translates into tangents that are, different values left and right, with a maximum in the middle. Is it clear? I can exaggerate. So it goes like so, and then smooth, and like so. And this is continuous with a maximum here. At points B and C, the tangents have different values. All right. It's zero order continuity, yes, but first order discontinuity, second order like this. If I want the maximum, or if I want the moments at the three locations, that's easy. It's going to be the area of a trapezoid. So moment here is going to be 1.29 plus 1.05 times 0.24 over 2, area of a trapezoid. Do you remember the formula to calculate the area of a trapezoid? So trapezoid, if I have a trapezoid with A and B and H, area is going to be A plus B times H over 2. Our trapezoid happens to be this type, but likewise applies. All right, area of a trapezoid. If I want the moment, which the maximum location in the middle, the maximum moment, M max, this is going to be area of the trapezoid just calculated plus the area of the triangle. So it's going to be whatever this is, never calculated, 0.24 times parenthesis 1.29 plus 1.05 close parenthesis equals, all right, so this is 0.2808 kilonewton meters, and to this I'm adding area of a triangle, so plus, so 0.2808 plus the area of the triangle, and the area of the triangle is going to be, we said that this is 0.6, is that correct? Was it? Yes. So I have 0.6 times half of this, which is 0.3 meters over 2. All right? So plus 0.6 times 0.3 over 2 equals, this is 0.3708 kilonewtons, the maximum bending moment on this beam. All right? Was it okay? All right, it's 1 o'clock. I need to do a couple things. Bring you the cover pages for the homework. So I'm pausing the recording. And then took a short break. So we're going to go over a problem with beams made of sections. And and we're paste. Again, problem is 84, so I need to write 84. It has to be within my reach to where I can draw. So 584. Okay. So I started saying this can very well be a machine component where you have a gear and another gear that's loaded with a helical gear with a radial and thrust load, and helix angles are on the other side. So it says for these problems here, the bearing that is resisting, so with a cross there are bearings, and then the bearing that resists thrust is, for our case, would be this one. All right, so we have bearings here, and this one resists any unbalance of forces, and there appears to be unbalance of force. So I have 20 degrees, one is bigger. The whole thing has a tendency to slide to the right. Will be this bearing that resists thrust. Okay, and then it says break the beam into components. Show the complete free body diagram on each component part, including all external loads and internal force and bending moments required. Keep the part in equilibrium. For the main horizontal part only, draw the complete shearing force and bending moment diagram. Refer to section 510 for examples. Okay, so if we were to delimit or isolate just the horizontal piece, I need to show the other end where the separation happens is I have a welded connection that introduces in general two forces at a moment. Okay, so what would be a good place to all right, so I'm showing the horizontal piece and it's 6 inches. And it's where I have the force at 20 degrees. And this is 125 pounds. And the angle is 20 degrees. This length here is 16 inches. And then I have the horizontal piece. I'm showing it here, displaced. The horizontal piece. Let's see. Got it. Of course, I'm not done here. I said there's a, so I need to show the reactions, and then there is a moment. I represented both, but I know their orientation. It's rather easy to use intuition. So I have to have the vertical component is going to balance by this one, horizontal component by this one. It has a tendency to rotate the, relative to the horizontal part, rotate them in this way. I need to add a moment M. It will be A, B, C, and D. Okay, so moment at A. If I move here, I need to flip these forces, so it will be R, AX, R, AY. So I need to flip them. There's a notation that can go you go like 1/2, and then you flip 2 to 1, and you recognize they're opposing. So if I put a minus here, because this will be the main one that we'll be analyzing, I can call this R, AY with a plus, in R, AX with a plus. Does it make sense? And then the moment, MA, put a negative and represent it here as a moment that is in the opposite direction, M. MA. Does it make sense what I did? So the orientation here are valid to balance the external force 125. When I move to this one that I know I'm going to analyze in detail, I put minuses here, and I'm going to call them by their name, RAY, RAX. Okay. All right. And then I can do the same for this one, represented here. And that's also, well, this is 14 inches rather. And so I have a force that goes 180 pounds. And this is 20 degrees. And in order to balance, I need to have a force here that's R dy, and then this force has to be balanced by a force that goes horizontal, R dx.
20 degrees the other direction.
Oh, it's 20 degrees the other direction. You're right. 20 degrees, no problem. We can account for that. So this is just the, so this is 180 pounds and the 20 degrees. Okay, so it means that I need to flip this force. Okay, I take them with a change sign. So this one has to go up, and this one has to go towards the. So this will be R dy, R dx, and I call them negative dy and negative R dx. Okay, so this is our beam, and then again, this will be for our main or of main concern. So I have point B, and I have point C here, and it's where RB and RC are, and we need to calculate them. Yes.
Just a quick question on the first segment.
Uh-huh.
When you go to the straight line, why is the RAY horizontal?
Why is okay? So RAY, you say? Why is horizontal?
Yeah, on the straight pipe, the middle piece.
Well, it's just a mistake.
Oh, okay.
What do you think?
I don't know.
Main mistake is human. There's another one. Only those that don't work don't do mistakes. They're looking for soft jobs. You don't do mistakes, you don't work, you have an easy life until recession strikes. 14 inches. Okay, so we can, going with writing equilibrium equations. And by the way, I need to also show a moment here. Is that right? So the beam, this short, the vertical portion at D has a tendency to rotate this way. I need to counteract with a moment it goes the other way. So this is M at D, and I call it negative. And I need to move it here, flipped. So it needs to go this way, M at D. Again, we're going to draw a shear force bending moment diagram for this guy. We can calculate these reaction forces. I'm going to populate this graph with values, okay? What is RAX that goes into on this figure? So this is the graph that I'm going to populate with values. It's going to be 125 times 20 cosine. So this is 117.5. 117.5, and units are pounds. Okay, I'm looking at this other one, and it's going to be 125 times sine. 125 times 20 degrees sine equals that. This is 42.8 pounds. Okay, and as for the moment, the force that causes or rather of the x and y component is the x component does a moment, and the arm of that force is 16. So it'll be this one here times 16 gives me the MA. All right, so 117.5 times 16 inches, it's 1880 pound inch of moment. Was it clear? Okay. And I move to this other vertical portion of the beam. So the horizontal, the x component of RDX that shows on this graph is going to be 180. So 180 times 20 cosine equals, this is 169.1 pounds, and the one that projects with sine, so 180 times 20 sine equals 61.6 pounds. And then the moment is going to be which force? It's going to be the horizontal force. Oh, I still have it. Actually, no. Calculate it first. So 169.1 times 14 equals, that's 169.1 times 14 equals, yeah, this is 2,367.4. 2,367.4 pound inch. Okay. So now we have and I cannot slide this up, but I can repeat the diagram rather easily. So now we're good to calculate the reactions at the bearings. Again, there's a bearing here and a bearing here. This one takes the thrust. So let's see what their values are. I'm going to some moments about point B, assuming positive to be counterclockwise, my choice, in order to calculate RC. So what do we have? Again, this is the pinpoint. So I have, starting with MA, and it's in my positive counterclockwise, so it's 1880. And then I have the moment, the axial, the X forces do not produce moment. So I have RAY 42.8 times the distance AB, which is 16 inches, times 16. And this causes a positive moment, so make sure it's a positive. Or rather positive, no, it's a negative for this convention. So it's a negative. Yeah, I had it negative. Okay, I move to this side. The arm at 35 forces RC causes a positive. So RC causes a positive moment times 35 inches. And then lastly, I have the RDY causing likewise a positive moment, so 61.6 multiplied by the full length. So 35 plus 16, that's what? 35, 45, 51 inches equals 0. This allows us to calculate RC. And then we'll take care of it in just a little bit. I'm summing moments about point C, have equilibrium, and we'll go which way? So firstly, and I forgot this one. This one 2x. So I also need to show a this way, this way, this way. Oh, if this goes this way, this has to be the other way. So this changes things a little bit. I have a minus here. Do you understand why? You saw that earlier? This moment was represented as clockwise. No, was good before. Yeah, it was good. I'm sorry. So clockwise, counterclockwise. but I need to include this into the equation. So I need to add 2367.4 equals 0. You could start with the moments. Again, moments are floating vectors, can be
Real quick, could you show us how to do the moment on that? I'm getting a little-
moment for D. What do you mean? How I got moment?
Yes.
Okay, so you just look at I have this arm and I have the horizontal force. The vertical force is not causing a moment. So 180 times cosine of 20 degrees times 14, it should be this value. Was it? 180 times 20 cosine times 14.
Yes, yeah, yep.
Okay, so one more time. Clockwise, counterclockwise. Clockwise, counterclockwise. Moments are good. And my counterclockwise is positive for my choice of moments. Okay, and then I sum moments about C. So I'm going to see, again, you could put both moments first. So it will be 1880. And then I have negative 42.8. And the arm is 51. And it's a negative moment. And then I have negative RB. Arm is 35. And likewise, clockwise, opposite counterclockwise. And then I move to this side, and I have a positive 61.6 times 16. Okay. And then I have plus 2367.4 equals 0. Okay. So from these two, I can extract or calculate RB and RC. We're using sum of forces in the y direction to verify. I should add to this diagram, so there is an unbalance of axial loads, which means that at C, the bearing at C is going to take up the difference between these two. So here at RC horizontal is going to be the difference between these two. Okay, so I say 117.5 negative 169.1 equals. So this is 51.6. Does it make sense? So this force plus this one here counteract this force here. This comes from the external force. This is the bearing force. Okay. All right. So let's calculate RC first. I'm going to move everything to the other side. So it'll be 1880 negative. And then I have plus 42.8 times 10. That's 428 and positive. 428. And then I have negative 61.6 times 51. And I have negative 2367.4 equals. Everything has to be divided by 35. Okay, so it looks like it's a negative value, negative. So I have R C is negative 198.885. I could say 9 pounds. All right. From the second equation, I move this to the other side, so everything stays with their sign. 1880 negative 42.8 times 51 plus 61.6 times 16 plus 2367.4 equals everything divided by 35. So I have 87.1.2 pounds. Okay, so let's see if I'll have to flip this force, but first let's put a negative value. 198. No, I'm sorry. This is negative. RC is the one that I need to flip. 198.9 This other one does not change, is 87.2. Okay? So we sum forces in the y direction or in the vertical direction. See if they go to 0. If they don't, we miss something. Okay? So 42.8 plus 87.2, 87.2 negative 198.9 plus 61.6. I have a residual 7.3. Did my roundup propagated that horribly? Or we missed something? It's too big. 7.3 pound difference.
I think.
Let's try this one again.
I think on the sum moments around B, I see 42.8. I think that's a 10. And it should be 16.
Yes, and I took it at 10. That's where it's coming from. Yeah, I made a 16 like a 10. Thank you. Okay, yeah, all right, well. So let's try again. Everybody on their own. 1880 times 16 plus 61.691 plus 6, 7. 191.5. 191.5 negative. Okay, so with this, I had 7 pounds difference. It's verified. We'll need to reorient this force. I make it positive here. That will change this to negative. It will change this to positive. Okay, so force verified. I can invest in drawing shear force and bending moment diagram, shearing force bending moment diagram for the horizontal piece. Was it clear? Okay, so I'm going to redraw this like here. All right, so, and no horizontal forces. For that, we can draw a axial load diagram. We'll do it after this. So I have 42.8, and then the moment. I need to show the moment. It's 1880, and this is point A. I move to point B. This is 87.2, and I have point C, and it's a force that goes down, which is 198.9, and then I have the end force D, vertical 61.6, and then the moment going this way. 2367.4 pound inch, pound inch, pound, pound, pound. Could have moved this up. I can move this up. 198.9 pounds. What about this? We're used to put the arrows at the point of application. All right, let's show the shear diagram, shearing force diagram. So V, and well, units are pounds. So I have 42.8, and nothing happens. And then I have a jump from 42.8 by 87.2. So 42.8 plus 87.2. 87.2 equals, it goes to 130. Let me make this smaller. And it's horizontal. So it goes to 130. And then nothing changes until I get to point C, where there's a drop by 198.9. So negative 198.9 equals negative 68.9. Negative 68.9. Well, it's still not okay. because this doesn't add up to 0. So I have 68.9, I have 61.6. Have we missed anything else? Positive, positive, negative. You understand what I'm saying? So the diagram should close to 0. Yeah, it's off by, that's 7. Have I? Oh yeah, because this is 191. I never corrected here. Yeah, 191.5. A mistake that haunts you, 191.5. 191.5, and this is equal to negative 61.6, and the diagram closes. Do you understand? I forgot to update here, and I propagated the same bad value. This is the correct. Okay, so we've got we've got them, and I need some more space. So pounds and pounds. Let me draw the moment now. Moment diagram. Moment in units poundage. And I show the neutral axis. And let's not forget we have external moments now. So the diagram begins with a positive. So when you have rather, this is counterclockwise. So it's a drop of the diagram. So I begin with negative 1,880 because of this. Does it make sense? And then I have, linear with a positive slope of 42.8, not too big slope. And let's see what it gets us when you get to point B. So negative 1880 plus the area under the shear diagram. So I have 1,880 negative plus 42.8 multiplied by the 16 inches. And 35 times 16. Okay, so I have, it's still negative. It went to negative 1,195.2 with a slope of positive slope 4.2. Okay. And then the slope increases to 136 pounds, and it stays linear until we reach point C. So let's see what's the value of the moment at point C. I have this already on my calculator. This is a decimal point. So there will be plus 136 times 35. And this is, it went positive to 3,564.8. So 3,564.8. Okay. So this is, and it intersects the horizontal axis, which was the beam will have maximum deflection. And this is, the shear diagram has just 1, 0. A C intersects or it goes to 0, so where I have a maximum. And diagram closes to, okay, you can, so still have this value. And subtract 61.6, negative 61.6 times 16. Yeah, it should be. I'm sorry, it doesn't go to 0. We have this moment. So it goes to, and the what? Is likewise counterclockwise. So the diagram will drop to 0 immediately after point D. It should end with 2367.4. So let's start again. We have this moment. I need to punch it again. 3,564 point. I think was a what? Was this a 5? Whatever it is, 4 or 5. And then negative 61.6 times 16 equals. And after point D, the diagram should close to 0. Due to this concentrated moment, we'll drop the diagram. It's counterclockwise. Is this value confirmed? And the n value should be 2,367.4, or very close. If you want to know where the diagram goes to 0, we can use similar triangles. I can call this A, I can call this B, my preference, my choice. You say A plus B equals 35, and then you say A over 1195.2 equals B over 3564.5, I call it. Might not be this way. And you get A and B. You can flip this if it might be more convenient to work with it this way. All right. Was it clear what we did? So what was extra were these concentrated moments, and almost missed the second one here. You can put them first. Again, moments have the same effect overall, not in terms of the beam response, but when you sum moments, you can assume them being anywhere. Okay, so we have concentrated moments, and that caused these jumps on the diagram. I said I can draw a what? In addition, I can draw a axial load diagram. And so if you go anywhere up to this point C, you see a compressive force of 117.5. So compressive, it goes below. And then here I have an increase of the compressive force to going to 169.1 negative, starting with negative 117.5. So this is axial. We sometimes put signs. So this is negative, this is positive. Okay. I'm not very happy with I think we missed something, or due to round off. It doesn't close crisp to 0 immediately after D, but this is it. That's why the bonus points in exams. (138) Questions? Don't forget the sample problems in the book. That's why the book it's 900 pages, 834 pages. By the way, have you noticed my name on the back? Have you? Yeah, my name is on the back. Yeah, but I'm sorry? Yeah, the physical book. If you have the hard copy, I don't think they included, they took me off on the 7th edition. Is everything. Have you been to Madame Tussauds in London? Or the Wax Museum? So they always keep the popular figures of the moment. And so Margaret Thatcher, they took the head off. It's on storage. It's no longer on display. They recycle the frame of the body and clothes maybe, or they're on storage. But when I was there was a few years ago. Arnold Schwarzenegger and that guy Home Alone as a kid. What is his name? Macaulay Culkin. Anyway, so yeah, I don't know how I started. I started with my name on the 6th edition. That's why we still teach you off the 6th edition. No, I'm joking. All right, so questions?
It's not bad, it's just initial setup. Just trying to figure out that first.
Well, again, don't forget the sample problems. Don't forget to try problems on your own. It's like, I keep on saying, it's like understanding a language and speaking a language, a foreign language. I'm a little this. Yeah, it doesn't have the, I went all the way to the back of the book. And the cover is not. Regarding chapter 6, that I assign a homework out of this chapter 6. You saw this in statics. I'm not going to emphasize it as much. The problems here tend to be a little more involved than what we'll actually see. And the computer-based assignment to you is more along those lines. So you can see a fabricated I-beam made of two tubular pieces or two pipes with a web welded in between, or you have two box tubings that were welded. Anyway, so I did this demo. Oh, by the way, here's a curve beam, and could induce loads to it. Anyway, so when it comes to bending, resistance to bending, if I bend this flat, could be with a force in the middle, which I'm trying to induce it somehow. It's one thing, but if I rotate the section 90 degrees, it's much stiffer. I'll not be able to easily bend it. I could right away bend it on the flat if I load it on the flat surface. So that's why we study area properties. And then, of course, finding centroids is likewise important, because you'll see in bending of beams, and also for torsion, but torsion we do only tubular and solid round. We don't do or machine components that are subject to transmit torque are either solid bars, round bars, or tubular. But the centroid of a cross section is where there's no stress due to bending. I'm sure everybody has broken a stick. You're doing breaking wood for a campfire. To break it, you hold it against your knee and you pull, right? So, and you don't do it towards it, you put it in the middle. You know that this is how you can maximize the load and break the stick or the, yeah. And when you do, everybody notice that the outside fibers pop and the inside, they pop. The inside may respond visibly, but the outside is it's popped or break due to tension. So the stress distribution in bending is max when I have a negative bending moment. So I can also break a thin stick by applying twist at the ends, right? So it's now I break it because of the end moments. Here I break it because I have a force in the middle and I resist with force at the ends. Now I apply rotation at the ends. Okay, so the outside fibers are in tension. The inside fibers are in compression. Okay. It might not look straightforward. If you have a bracket on the wall, like this one here is, and I apply force from the top, these upper screws are going to be resist pulling from the wall. The bottom one, they're not. They're forced against, or they don't carry, but the direct down shear. So the bolts are subject to shear parallel to the wall, and the top ones tend to be pulled from the wall. The bottom one, they don't experience that because it's the bracket itself that press against the wall. All right. Again, just anticipating, this kind of analysis are relevant for building frames with flange mounted at the in between and such. Okay, so that's why the knowledge of the centroid is relevant, because they are the neutral axis. If the beam has symmetry, the cross section has symmetry, and there are various cross sections here given. Not that all will be I mean, even these awkward ones might be, you know, architectural elements for decorative parts, but also carrying load. So if the beam has symmetry, the centroid is always going to be in the symmetric center. If the symmetry is uniaxial, like here, all are symmetric. So axis of symmetry, centroid. Centroid, okay. If I have a T section, though, let's see, like this one, it's more than a T section. The centroid will be on the vertical axis of symmetry. I cannot find the axis or horizontal axis of symmetry, but I know how to calculate the location of the centroid the way you learn in statics. Is that correct? If I have missing material, you know, so I divide this into sections that I know they're centroid, and I can calculate areas. And you go appendix 1 at the back of the book. So where's the centroid of just this top part number 3? In the middle, you draw the diagonals, and it's where the centroid is. And then I can take this missing part, where it says part 2, as a negative area. And in my analysis, I'm just going to make it as a negative area. And then part 1 is going to be one big rectangle. The alternative being to take only positive areas. It will be 1 and 2 and 3 and 4. Too many to, or, you know, easier to go with a negative area like it's shown here. There are ways to finding the center. I'm just telling you here, maybe you've been told in statics. So you have a irregular plate, shaped plate. You can find the centroid by hanging it on 2 spots. So the center of mass is going to be along the vertical through the support, through the pin, right? You draw a line, and then you hang it from the other one. Draw this other line where the 2 intersect is the centroid. Could be any shape, any shape. Okay, so yeah, that will be one part, finding the centroid, and there are some tables that you can put your work system in a systematic form. So part 1, 2, 3 area, and then these yi are distances from what you assume to be a reference axis. Usually it's taken at the bottom to work with positive values. So you go, and what is the centroid of the top part? Will be 55 p is y3. Where is the centroid of part 1? Again, the the rectangle without the missing part is 25. That is half of this. And where's the centroid of part 2? 15. You populate this table. You evaluate the product area times distance from the chosen axis to the centroid of the individual parts. And you then take the sums, and then you divide by, so this is some area times distance to the centroid products, and then you divide this by this, and it gets you the centroid value y overscored. And here again, the reference axis was assumed to the bottom. Okay, so that gives you centroid. Now, moment of inertia of area, it's an integral, and in general, so moment of inertia about an axis is the integral of the distance from that axis squared times the small piece, infinitesimal piece of area. And in statics, you took, you know, either stripes and you moved along the y-axis. Sometimes you took little rings that you increased the radius to them, but their thickness was d, r, maybe. That integral will come up as we do equilibrium, moment equilibrium of pieces of beam, where you have stresses acting on both sides, and they are holding each other in equilibrium together with the reaction inside of the beam at that location. to find area moment of inertia that is needed in calculations with beams, stress analysis of beams. I have a bookmark. You can see the folded page. So the table on page 365, this is where we're going to go for the most involved analysis. You'll do the same for the hand calculation part of this homework one. So this is the table. You can be more than 3 parts, yes. And we have, so the first up to here, we calculate the centroid. So part 1, 2, and 3, its area, the distance from the axis to the, it could be sign number, could be positive or negative. If the reference axis is somewhere, it could be above or intersects the part. Usually we take it at the bottom level for all these values to be positive. And evaluate the product, and this is what the earlier table will look at just for the centroid. You sum areas, you sum products, area times distance from the axis to the centroid of the individual shapes, individual parts, and then you calculate the locate or distance to the centroid. All right, this is assumed, you see only y here. Why is that? Because we usually have, it's not of interest to us to know where the centroid is on the horizontal axis, or maybe it is because later in the chapter, in the next chapter, which is 7, we discussed loading of shapes that don't have vertical symmetry. And you don't want to, as you load a piece, you don't want to induce twisting with bending. That it's a useless additional stressing of the part, if it makes sense. Okay, it's like having a column, if you can watch. So I have a column, and instead of loading it axially, I load it on the side. And loading it on the side adds bending to the column instead of just compressive load, and that can anticipate or cause failure earlier. It does not hold the same amount of axial load when you add bending by shifting, not having centroidal loading. Okay, so for area moment of inertia, to calculate area moment of inertia of the assembly, you get this centroidal moments of inertia of the individual shapes. So for that, you go to the back of the book, Appendix 1. So you have rectangle, circle, whatever shapes, half a disc. These are all centroidal figures. They're the smallest. So area moment of inertia is about an axis. Its minimum is the axis passes through the centroid, if you remember. And then I have, in anticipation for what is called parallel axis theorem, because if the axis about which you evaluated the area moment of inertia is not centroidal, the moment of inertia is going to increase. That the distance is squared here. Again, the parallel axis theorem, I'm sure you've heard of parallel axis theorem. Likewise in dynamics, when calculating mass, working with mass moment of inertia, use parallel axis theorem. Okay, so these are centroidal values. You calculate the distance from the axis that you considered. Actually, no, let me back off a little bit. So you see here the distance between the centroidal axis that you have, you know where it is now. So you started with an arbitrary axis, now you move to the centroid, and you calculate the distance from the axis through the centroid to the centroid of the individual pieces. These are the values. And then you multiply with the area, and you square multiply with the area. Okay. And then it shows like, a full parallel axis theorem. So this plus this gets you this. And then finally, to calculate the total moment of inertia, you sum this last column. Is it clear? So again, I have it bookmarked, the table. You'll see me going to page 365. Easy to remember, number of days in a regular year, or Windows or Office 365, whatever. Okay, so we've got area moment of inertia. And that's going to be used in stress analysis. We're going to do this again when calculating shear forces caused by bending, but that will be for, I think it's chapter 9. Okay, because we may be interested, you have a fabricated section, you want to know what the shear stress is caused by bending at the interface between the two. All right, say you use fasteners, how are those? Or maybe use glue or weldment, you want to calculate this. But for now, for bending moments, we're going to make use of just the area moment of inertia about the overall centroid. Okay. And yeah, the things that you've seen in statics, I'm not sure if it was an excuse to apply integrals in calculus likewise. So again, definition of the area moment of inertia is distance squared times area. What would be the area we scan was stripes, so dy times the constant b. And again, the definition of was integral of the moment of inertia. Very well, integrals, when you have a domain, you can distribute, so some integrals over subdomain gets you the integral over the entire domain. You've seen this in calculus. Yeah, here's an example of a fabricated beam. So we have an I-beam, and it's and because you have added plank or plate on both, the centroid will be in the middle. So you can start